Example 5.3.4. This one says you took out a $200,000 loan exactly 5 years ago.
Okay.
The loan required monthly payments of $1,330.61 for 30 years, had an APR of 7%, and you just made the 60th payment. Interest rates have fallen over the last 5 years, and you could take out a new loan today at a 3% APR with monthly payments. You would like to refinance the original loan with a new one that has lower monthly payments. That is, you would like to take out a new loan that will exactly pay off the remaining balance of the existing loan. How much will the new loan be for? That is, what is the balance on the original loan immediately after making the 60th payment? All right, we've got another time value money problem, so we're going to use our three-step process again, where first step is mapping out the timeline of the cash flows so we can figure out what kind of cash flow we are dealing with here. Once we know what kind of cash flow we are dealing with, we can select the tool that is best to evaluate this particular type of cash flow. All right, so there's kind of a lot of moving pieces with this one. We had a loan for $200,000 that we took out 5 years ago. The original loan was for 30 years, but we've been making payments for 5 years. Making monthly payments for 5 years. So that means we've made 60 payments over the last 5 years. 5 times 12 is 60. The timeline that we're going to draw, though, is not for that original loan. The timeline we need to evaluate is what payments remain on the loan. And the reason we want to look at that is because the balance on a loan is, the way you find the balance on a loan is by finding the present value of the remaining payments on that loan. And that's a trick that we'll use over and over and over again. When we need to figure out the balance on a loan, we'll just map out the payments that have yet to be paid. We'll find their present value using the interest rate on that loan as the discount rate, and that'll tell us how much we still owe on the loan. So the timeline we're going to map out is the timeline for the payments that have not yet been made. Not the original loan, not the ones that we have already made, but the payments that have yet to be made. So today, right now, is actually 60 months into the loan, or 5 years into the original loan. And what we want to find is the balance that we owe right now, right? We've just made a payment, and we want to know what is left on the loan. So we're going to map out the payments that are left. So 1 month from today, remember we've just made the 60th payment. We're going to make the 61st payment 1 month from now, or we would make the 61st payment 1 month from now. So this 1 is actually 5 years and 1 month into the loan. The payment, if we were going to make it, I'm going to look at this from the perspective of the borrower. So it's going to be a cash outflow of $1,330.61. Oops, $330.61. There we go. And then a month after that, we'd make another payment. And then that pattern would continue out to how many months? How many are left? So the original loan was for 30 years with monthly payments. So the original loan had 30 years times 12 payments per year. That was 360 total payments. But we're 5 years into this, or 60 months into it, and so of those original 360 payments, we have made 60 of them. So we'll subtract that out and find that we have 300 payments left to make. So if we were to continue paying on this loan, we would make an additional 300 payments of $1,330.61. All right, we still need to put the interest rate on the timeline. And importantly, the interest rate that we use here has to be the effective rate that matches the same time period over which we're making payments. Since we're making monthly payments on this loan, we need to use the monthly effective rate for this loan. And the interest rate on this loan is the rate that we were paying on the loan, not what we could refinance it for. That loan doesn't exist yet. To find the balance on this loan, we need to use the rate that applies to this loan. So in order to find that, we'll use the definition of APR, because all we're given is the APR. We got to find the monthly effective rate, where the APR is equal to little r, that is the periodic effective rate, in this case the monthly effective rate, times m, which is the number of compounding periods per year, or the number of payments per year. Those two are the same thing with an annuity. We know the APR, that's 7%. Little r is what we're trying to solve for. And we know that we're making monthly payments, so it's 12 payments per year. So to solve for little r, we'll just divide both sides by 12. And I'll move r over to the left-hand side, since that's how we're used to looking at variables that we're solving for, just having them on the left. 7 divided by 12 equals 0.5833. And I used 7 there, so it's already in percentage format. So that 0.5833 is 0.5833%. All right, so we've got all the information on the problem, from the problem on the timeline. What we need to do now is figure out what type of cash flow we are dealing with. We already know that we're looking for the present value of this thing. We got to find the present value of the future cash flows. But in order to solve for that present value, we need to select a tool that we can use to evaluate it. And the tool that we use depends on the type of cash flow that we're looking at. Well, we have level payments, right? It's the same $1,330.61 over a period of 300 months. It does stop, so we know it's not a perpetuity. We could, of course, treat it like a lump sum, because we can treat every cash flow like a lump sum, but then we'd have to deal with each cash flow individually, which would take a while. So if we can figure out if this is one of our 3 annuities, we've got some shortcuts available, either the time value of money keys or the formulas associated with annuities that are a lot easier than dealing with each payment individually if we're going to treat it like a lump sum. So we have our 3 types of annuities. We have an ordinary annuity, Annuity Due, and a growing annuity. And we'll start by a process of elimination. The third type, a growing annuity, if I look at our cheat sheet here, those cash flows change over time, and they change at some set rate. They may grow at some set rate, and they may shrink at some set rate. And that's not what we have going on with this cash flow. It is a level cash flow, so it's definitely not a growing annuity. We can cross that one off. The only other 2 options are an Annuity Due or an ordinary annuity, where the difference between those 2 types of annuities are the timing of the cash flows. With an Annuity Due, the cash flows happen at the beginning of each period. So if we look at a timeline here, we can see the payments happen starting at time period 0, at the beginning of month 1. And then they end at the beginning, in this case, of year or month 3, whatever the periods are here. But it happens at the beginning of the period, and we've got this blank spot on the end of the timeline, because that last period still runs out, but the cash flow has already happened. An ordinary annuity has cash flows at the end of each period. And so the first cash flow is at the end of period 1, and the last cash flow is at the end of period 3 in this case. And this looks more like what we're dealing with here. If we look back at our timeline, we just made a payment today. We're looking for the present value today, and the next payment doesn't happen until 1 month from today. So they're happening at the end of each period. So we're dealing with an ordinary annuity. Once we know we're dealing with an ordinary annuity, we know what tools are available to us. We've got the present value, future value of ordinary annuity formulas. We've got the time value money keys on a financial calculator and a spreadsheet available to us. We're going to sidestep the spreadsheet, though those solutions are available in the text, and I encourage you, just for outside of class use, to take a look at those, because it's a lot faster and you can do a lot more stuff with the spreadsheet. It's just that they're not typically available on exams, and I know most of you using these videos are going to be prepping for exams. So you're going to be using either the formulas or the calculator. In this case, I would imagine most folks are reaching for the calculator, because we already know we're looking for the present value of an ordinary annuity. We've got the formula for the present value of an ordinary annuity there. And it's not overly complicated, but there are lots of opportunities to make errors with either order of operations or just kind of typing in the wrong thing. And so a lot of folks I know will reach for the calculator because it's a little quicker and a little less likely to make mistakes with. So we're going to jump right into the calculator solution for this one. as usual, I'm going to write out the calculator entries in the same order that they appear on the calculator. On the calculator, I'm going from left to right. On my page, I'm going up and down. No magic to that. That's just a habit I got into as an undergraduate and stuck with it. Feel free to come up with your own strategy. Just to make sure, I would encourage you to pick a consistent strategy to use over and over again, just to make sure that you get all of the information in that you need to get in. It's too easy to miss something if you're using a different way to track all the information every time. All right, N is the total number of payments on this one, and that is 300. We have 300 payments remaining. I over Y is the interest rate. In this case, since 300 is in months, it is the monthly effective interest rate we want to put on there. And that is, we've already found 0.5833, but we want to be really careful here. If we just type in that 4 decimal approximation, we're going to introduce a pretty significant rounding error, because if we look at the formula, that R here that appears in the formula is raised to the N, where N is the total number of payments or total number of compounding periods. That is 300 in this case. So N is 300, so any error in R that we introduce is going to be magnified exponentially 300 times. That can throw our answer pretty far off. So we want to be as precise as possible with R. So what I'm going to do is actually have the calculator solve for that 7% divided by 12, and I'm going to use the as precise an answer as is available in there by having it do the division and then using the value that it calculates there, because it'll work it out to 13 decimal places. Present value is what we're looking for, so put a question mark there. Payment, we're looking at this from the perspective of the borrower, so that's a cash outflow of $1,330.61. I'll record it as a negative. And then future value, we're going to record as 0, not because the future value of this annuity is 0, but what we put on these cash flow keys, PV, PMT, and FV, are the cash flows that happen on the respective parts of the timeline. Present value is what happens at time period 0. Payment is what happens over and over again at each of the tick marks. And then future value is what happens at the end of your timeline. Now, of course, we do have a payment at the end of the timeline here, but we have already accounted for it when we say payment is $1,330.61 and we get 300 of them. So the calculator already knows about that last payment. We would only put something on the future value key if there was another cash flow here in addition to that last payment. In this case, we don't have that, so that guy's going to be 0. Okay, let's plug these in. I'm going to start by clearing out the time value of money keys, which will record zeros on all the keys. So second clear TVM. We'll zero everything out, and then I'm going to enter them left to right. N is 300, so it's 300, and then press N to store it. I over Y is that 7 divided by 12, and I want as precise an answer as I can have here. So I'm actually going to type in 7 divided by 12 equals, and have the calculator do that division. Now I know it's showing me 4 decimal places because that's what I have my calculator set to, but it is actually worked out to about 13 decimal places internally, and if I will press the I over Y key while this number is on the display, it's not actually recording that 4 decimal approximation, it's recording that full 13 decimal version. So that's much different than me typing in 0.5833. By having the calculator do the division and then press the I over Y key, we get a lot more precise answer. And PV is what we're looking for, so we'll skip over it. Payment is $1,330.61. Hit the plus minus key to make it negative, tell the calculator it's a cash outflow, and then press the payment key to store it. And then future value is 0, which it should already have 0 recorded there since we cleared it out. But just to be sure, I'm going to go ahead and type 0 and then FV to store it. Okay, we have 4 of the 5 variables. We can solve for the 5th, which is present value in this case, by hitting compute, PV, and the balance on this loan, the amount that we owe right now, after making 60 payments, is $188,263.89. All right, so if we were to put that on the timeline, just so we can have a sense of what we actually calculated here, what we just found is that the present value of these 300 remaining payments is $1,888,263.89, which is also what we still owe on this loan. So if we wanted to refinance the loan, that is pay off this loan with a new one that has a lower interest rate, we would have to borrow $188,000, a little over $188,000 in order to do that. Now let that sink in for just a second. We've been paying on this loan for 5 years. We originally borrowed $200,000. All right, so we have been, let's just see, let's subtract that from 200,000. So after making payments, 60 payments over 5 years of $1,330.61, we have managed to decrease the amount that we owe on this loan by just $11,736.11. That's kind of nuts. And that is the effect of compound interest over time. It's a long-term loan, and so the amount of interest that we're paying over time is huge. And that interest is kind of the rent on the money. We're just paying that to the bank because they let us use their money to make this purchase, and we've got to repay them for that. The amount of principal that we're paying back is relatively small up front, although it does grow with each payment, and we'll look at that in later chapters. Just for fun, how about let's take that payment amount, the $1,330.61. We were going to make 360 of those payments, so I'm just going to take this value and multiply it times 360 so that we can see the total dollar amount that we're repaying. Of course, this totally ignores the time value of money, right? So this is not necessarily a theoretically sound thing to do, but it does give us a sense of we borrowed $200,000, how much did we end up paying back? And although we borrowed $200,000, over the next 30 years, in nominal terms, we're going to pay back $479,000, $479,019.60. So over twice what we borrowed, which is kind of nuts. But that is the power of being on the other side of compound interest. If you're investing, it's an incredibly powerful positive force. If you're borrowing, it's a really positive force for the person who loaned you the money. It's kind of tough for the one who borrowed it. So that's definitely something to be aware of.